Okay, in the previous section we talked about limits that were infinity, so the answers were infinity or negative infinity. In the next section we're going to talk about limits at infinity. And when you talk about a limit at infinity, it's going to be a value that a graph approaches, or f of x approaches, as x increases or decreases without bound. So if x keeps getting bigger or smaller or smaller or smaller, which when it gets smaller it's getting more negative, then what happens to the graph? What happens to the function? Where does f of x, where do the y values go? So in general we write this, the limit as x goes to infinity or negative infinity of some function. Now you get this a lot when you think about a fractional function. So if I think of the term k over x, so some number over x. Well, if I'm thinking the limit as this goes to infinity, really what I want to think about is what happens to k over infinity. Now, of course, k over infinity, it doesn't make any sense. It's not a real thing. You can't just divide by a symbol of infinity. But what we can think about is if we think the bottom of a fraction getting larger and larger. So k divided by 10, or k divided by 100, or k divided by 1,000, or k divided by 10,000. Well, as the bottom of this gets bigger and bigger and bigger, all of these get smaller and smaller and smaller, and they approach 0. Now, of course, they never get 0 because you can never take 1 and divide it by a super big number and get 0. But with a limit, it actually tends to go to 0. We can actually generalize this, and in general, as limit as x goes to positive or negative infinity of some number over x to the nth power, because if I raise it to a power, it's just going to get bigger and bigger and bigger, is always going to be 0. So the limit of any number over x to a power is going to be 0. So we can use these to find some limits if we kind of practice rewriting them in a slightly different form. So if I look at this first one, it says the limit as x goes to infinity of 1 over x plus 2. So if I look at this, this is essentially 1 over some really, really big number plus 2. That doesn't really help us. So what I'm going to really do, though, is I'm going to rewrite this. And what I'm going to do is I'm going to take each term in this limit, and I'm going to divide it by the highest power of x. Now, the highest power of x is x. So if I divide every term by x, I get 1 over x, I get x over x, and I get 2 over x. Now remember, any number over x to any power as you go to infinity or negative infinity is 0. So 1 over x would go to 0. 2 over x would also go to 0. And x over x, remember, is just 1. So this limit is going to go to 0 over 1 plus 0, which is 0. So in this case, the limit of this function goes to 0 as you go off to infinity. Or actually negative infinity as well, because the same concept would apply. Alright, let's look at this next one. We have limit as x goes to infinity of negative 1 over 3x minus 4. Similar idea to the last one. I'm going to take the limit as x goes to infinity. The highest power is x, so I'm going to divide them all by x. So negative 1 over x, 3x over x, minus 4 over x. Now anything with a number on top and x to a power on the bottom is going to go to 0 as you go to infinity. That goes to 0. And this actually goes to 3 because the x's will cancel. So we get 0 over 3 minus 0, which is going to be 0 again. So as you go off to infinity with rational functions, you do get 0 a lot. But you don't always get 0. And that can be demonstrated in our next problem. So if we look at this one, I'm again going to infinity. Now the highest power in this case is the square. So I'm going to try to divide x squared to every term. X squared, 4x squared over x squared, and negative 5 over x squared. Now only the things that have the x to the power on the bottom are going to go to 0. So that would go to 0, and that would go to 0. Now here the x's cancel out, so this goes to 3. Here the x's cancel out, so this goes to 4. So if I put what I have left, I have 3 minus 0 over 4 minus 0, which is 3/4. So just dividing by these x squared, or these x to whatever power it is, can make it so you can take advantage of that limit of some number over x to a power being 0. Bigger and bigger. Now dividing by x is fine, and the highest power of x is fine, but there is a shortcut that we sometimes utilize when we're doing limits at infinity. Now this is only true for limits of rational functions at infinity, okay? So if I want to do the limit as x approaches infinity or negative infinity of f of x divided by g of x, then this limit you can actually find with a little smaller limit. You can do the limit as x goes to positive or negative infinity of the leading term of f of x divided by the leading term of g of x. Now what is the leading term? The leading term is the coefficient and the x and the highest power. So you're only looking at the term with the highest power in the numerator and the highest power in the denominator. Everything else you can just ignore. So this is a nice shortcut that you can make really difficult limits very simple. So if we look at this first one, it says, what's the limit as x goes to infinity of x squared minus 8x plus 12 over 7 minus 12x plus 4x squared. Now, only because we're going to infinity. This is only true when you are going to infinity. I can make this limit just the quotient of the two highest leading terms. So x squared is the highest term in this one, and x squared is the highest term in this one. So all I have to do is just take those two leading terms. So the nice thing about doing this in this case is you have the x squareds cancel. So this just becomes the limit as x goes to infinity of 1/4, which is just 1/4. So as you go to positive or negative infinity, we're going to 1/4. So let's look at this one. Now this one says limit as x goes from 2 from the left. Now, I put this one in here because a lot of people say, well, we'll take the limit as x goes to 2 from the left of 3x squared over x squared and cancel those out. This is not allowed. You cannot do this. The reason we can't do this is because this is not at infinity. That rule is only true at infinity. If I did want to do this problem, I would have to see, okay, if I plug in 0, what would I get? If I plug in 2, pardon me. If I plug in 2, I get 3 times 2 squared minus 5 times 2 minus 2 all over 2 squared minus 4, which gives me 0 on the bottom. And on the top, I get 0 as well. So 0 over 0, this is where I factor. So it's always important to plug in and see where we're at. But this one is one of those ones where we have to factor. So the bottom factors is x plus 2, x minus 2. And the top is going to factor as x minus 2, 3x plus x minus 2 and 3x plus 1. Yeah, there we go. So now these cancel. And so now I can just plug 2 in. So this is 3 times 2 plus 1 over 2 plus 2, which is 7 over 4. I just wanted to point out that not every time can you do this where you just take the leading terms, only when you're going to infinity. All right, let's go down here and look at this one. So this one has 2 terms. Now the good news is is this is going to infinity, and I have two rational functions added together. So the first thing I would do is I would go ahead and break this into two rational functions. So this is 3 over x squared. And then this one is going to be the limit as x goes to infinity of 2x squared over x squared minus 6. Now this first one is 3 over x to a power. So this one is automatically going to go to 0. Now as far as this one, it is a rational expression going to infinity. So this is where I can take the quotient of the two highest powers. And so that's just going to give me 2. So this whole limit is going to be 0 plus 2, so that should tend to 2. So a number over x to any power is 0. Otherwise, if you're at infinity, you can take the quotient of the leading terms. Let's look at one more. Now this one's a little different. This one is not a rational function, but this is something we can think about at infinity. So I have the 3. This is going to negative infinity, pardon me. So this is the limit as x goes to negative infinity of 3. That's fine. Minus the limit as x goes to negative infinity of 4 over e to the x. Now I write it as 4 over e to the x because remember a negative exponent means you can write it as a flipped fraction, so I can move it to the bottom. So the first one is a constant, so this is going to go to 3, no problem there. Now when I put in negative infinity here, negative infinity is actually going to essentially flip this back. So it's going to be 4e to a really, really, really large number with a minus sign in front of it. Well, it's essentially going to go to negative infinity, as big as you possibly want. So really we have 3 minus an infinitely large value. Well, 3 minus an infinitely large value is still going to be negative infinity. So this limit is going to tend to negative infinity. Again, for all these, a great idea is to graph it, see where it's going, because graphing can really help us out and kind of see what's happening. We can also look at limits at infinity of polynomial functions. So these are tend to leave in a polynomial function. These are tend to going to go to infinity or negative infinity in general. But we can find the limit of a polynomial function, f of x. That is going to be the same as the limit as x goes to infinity of its power function. Now remember, a power function is simply just the leading term of a polynomial function. So it's the x to the highest power and the number in front of it. Now again, these will typically, since they're smooth curves, they'll a lot of times go off to infinity or down to negative infinity, depending which way you go. Very rarely, if ever, will these ever flatten out and become like a real number. So for this first one, it says the limit as x goes to infinity of x squared minus 4. So we can just take away everything except for the x squared. Well, if I think of taking a really, really, really large number, a big number, and square it, it's just going to be a really big number itself. So this should tend to positive infinity because you're getting some really big number squared. If I look at this one, it says the limit as x goes to negative infinity. Now this is going to be negative 12x cubed because I just look at the leading term, power function. So if I plug this in here, then I'm getting negative 12 times a really, really, really big negative number to the third power. Now, if I take a negative number cubed, it's still going to be negative. So negative 12 times a really big negative number is going to be a really big positive number, which we would assume would be positive infinity. Now, if you think about what this graph looks like, the power function looks something like this. So as you tend going off this way into negative infinity, you can see how the graph is increasing without bounds, so going to infinity. So really just trying to see where the graph goes off in both directions. The last thing we're going to do is look at limits of piecewise functions, which is kind of Things we've looked at a little bit before, but we're going to talk about them at infinity and things like that as well. So if you look at this, so we have three parts. We have 1 over x minus 2 if x is less than 2. It's 8 if x is equal to 2. And it's 2x cubed plus 7x if x is greater than 2. So obviously 2 is going to be a pretty important number that's going to break apart our graph. So on the right side, when it's bigger than this, I have the 2x cubed plus 7x. And when it's smaller than 2, I have the 1 over x minus 2. Now I'm going to try to do this without graphing. It also has the point at 2, it's 8. So it's 8 there, but it doesn't really matter what happens at that point, because when we're talking about limits, it's all about what happens as you approach. So if I think about this first limit, it says, what's the limit as f of x approaches 2 from the right? Well, if it's from the right, then we're talking about this value here. So all I have to do is simply plug the 2 into that right-hand side and see if it gives me a number. If it gives me a number, it's a direct substitution, it's done. If not, it's probably something else that I have to do one of my infinities or something like that. So that's 16 plus 14, so that is 30. So the limit from the right is just simply 30. Now from the left, I'm plugging it into this piece. So when I plug in 2, I get 1 over 0. Now 1 over 0 is typically, when I see that, I'm usually going to get positive or negative infinity. So the way we did this is we said, all right, let's take a number that's slightly smaller than that, 1.99999, and plug that into 1 over x minus 2. So if I do that, I'm going to get 1 over a very, very infinitely small negative number. So 1 over a small number is going to approach infinity, and since it's a negative small number, this should be negative infinity. So from the right, it's 30. From the left, it's negative infinity. That will make the next question really easy to answer, because it says, what's the limit as it approaches 2? Well, that's simply going to be does not exist, because you can almost visualize it. In one side, it's going to 30, and the other side is dropping down to negative infinity. So the next one says 5. Well, 5 is somewhere over here. So that's definitely going to be in that cubic part. So I would just do a direct substitution, see if it gives me anything funny. And it shouldn't, because it's just a cubic function. So we get 2 times 5 cubed plus 7 times 5. So we just have to figure out what that is. So that's going to be 2 times 125 plus 35. That's 250 plus 35. That's 285. So as this thing goes to the right, you can kind of almost envision it. It was at 30 at 2, and now it's up to 285. So it's obviously increasing quite a bit. The last two talk about going to infinity and negative infinity. So infinity is obviously over here. So that's going to be with this 2x cubed plus 7x part. And negative infinity is going to be over here with this part. So if I'm doing to infinity, I'm essentially plugging a really, really big number in. It should be the same as the limit as x goes to infinity of 2x cubed. Remember, for a polynomial function, we just plug in, or we just use the leading term, the leading power function. Well, if I think about infinity in this function, I'm talking 2 times infinity cubed. So if I take the biggest number ever and cube it and multiply by 2, I'm going to get a really, really big positive number. So this thing should go to infinity. Now for the other one, I'm talking about going to negative infinity. That's going to be the limit as x goes to negative infinity, but it's going to be this left piece, 1 over x minus 2. Now, we can do this lots of ways. One way to do it is you can divide them all by x, or you could just say it's the leading terms, the highest power. So if I write this in terms of the highest power on top and bottom, it's going to be 1 on top and x on bottom, because that's the highest degree in the top and bottom. So remember, the limit of 1 over any x to any power is always 0 when you go to infinity only. So that goes to 0. And that's simply because that rule, if you remember from earlier in this video, x going to positive or negative infinity of any number over x to any power, any positive power, is always 0. So, now I could have, of course, graphed this piecewise function, but I just wanted to show you that you can do some algebra with it to actually just logic your way into a lot of these limits. So obviously, if you have questions on this, bring them to class, let me know. We'll go over them there for our last section on limits before we take our first test.